So now let's move to the second topic, which is pure Nash equilibria on uniformly related machines. So unlike the case of unique machine, of identical machines, the case we are looking at now allows for the machines to be uniform, so they are only different in one aspect, in the speed. So before, in the case of identical machines, we first bounded the price of anarchy, because we know that the price of stability is always 1. Or we prove that there is always an optimum Nash equilibrium. First, we prove there is always a pure Nash equilibrium. Second, there is always an optimum Nash equilibrium, an optimum pure Nash equilibrium. But the question of price of anarchy, of course, always something which worries us. So we first bounded the price of anarchy, and then we consider the computation of Nash equilibrium. We do the same now. Start with the price of anarchy and then move to the computation of Nash equilibrium. Of course, we will also compare to what we had before. So we can never get a better result, of course, now than we did before, because before we assume something which is basically a special case of what we have now, simply when speeds are equal. So for identical machines, before we proved that if you have an assignment which is a Nash equilibrium, I remind that strategies are basically the strategy of a player plays a task. Strategy is where the task goes, and therefore the strategy profile is an assignment. So an assignment being a Nash equilibrium implies that the social cost of that equilibrium was at most 2 minus 2 over m plus 1, m being the number of machines, times the optimum. So the price of anarchy was at most 2 minus 2 divided by m plus 1, and that was also proved to be tight. For any m, because we found an example, or we showed that we can find an example. Actually, there is an exercise for that. That this can be tight. Now that's what we have there. Now on uniformly related machines, when we don't assume the same speeds, but we assume any speeds, the bound actually may be above any given constant. So we cannot hope for 2 or for any other constant. We'll show that. What we will also show is that we actually can bound this growth by some slowly growing function of the number of machines. I remind you that there are n players identified with task, and m machines. This bound, this slowly growing function, we'll see, is actually tied up to a small constant factor. In particular, that means the last part means that it can be above any given constant, because this slowly growing function still grows to infinity. So we'll find that what we'll do actually for the price of anarchy, we'll first find an upper bound, and then we will show its type. And now here, the proofs are somehow long. That's why I will tend to remind you stuff. I will try to, like now, tell you stuff which you need to recall, and also you will see repetitions of the kind of the gist of what we did on the previous slide, on each slide. And if you still don't remember, of course, just stop the video and go back. That's why it's much simpler to watch videos than just to listen when you cannot go back. And if you don't understand, as usual, ask me in the comments. So the first theorem is the upper bound. So consider a load balancing game with n tasks of weights W1 till Wn, and m machines of speeds S1 till Sm. So here, and like we did before, we actually have different speeds. So then, an assignment is a Nash equilibrium implies that the social cost of the assignment is bounded by log m divided by log m. So it's a logarithm. The associated is from the right. It's a logarithm, and then we take a log of log. So that's basically the bound. And that's indeed a very slow growing function, because logarithm is a slow growing function. It grows much slower, exponentially slower than the linear function. Then the log of the log is also in a slower growing function. So here we have a logarithm, which not enough that we have a logarithm, we also make it slower by dividing it by some other function which goes to infinity. So very slowly, log of log. So it's a function which goes to infinity very slowly, slower than logarithm, but still it goes to infinity. Therefore, as I said you, that when the next theorem show that it's actually tied up to a constant, then we will also automatically show that no constant bound can be found, because that's still not a constant, but something that goes to infinity. So quite slowly. Practically, that can be a really good bound. Calculate what happens. Let's say if you take 1,000,000 and be million and log, it's log, right? Log, so 10 logarithm basis of 10. So 10 of million is 6. And the log of m, it's like log of a million is 6. And then log of 6 is log of 6 is what is the power of 10 to get 6. So it's less than 1, of course, but it's smaller than, so it's less than 1. So basically, it's going to be a bit more than 6 per million. You can play with it, but it's not very good. That's what I want to tell you. It's not very good. If you are at the class, we play with the numbers a bit, but you see what is. Yeah, but you can do it alone. That's something definitely. Do it alone and see how. Anyway, the factor is O off, so it can always be something within a constant. It's not really meaningful when I tell you 6 or 10, but you can see at least the growth rate, the rate of growth is small. So what we do is I want to give you the steps, because the proof is not hard. It's simply, as usual, the combinatorial considerations. And it's important to keep track of where we are. That's why I give you the idea of the proof. And then I will multiple times be reminding you where we are. So first, we prove the theorem quite quickly using a certain recurrent formula. So a certain recursive correspondence, which will say, okay, we'll prove it later. Given that, the proof is quite short. Now then, we need to prove the formula. That's what we have to do to finish the proof. And then we prove the basis of the formula of the recursion. And that's also going to be quite short. And then we'll prove the main recurrence. Again, by then you will maybe forget where we are, but I'll again I'm telling you, we are proving this important thing bound. We just have several steps. And to prove the main recursion, we'll need a lemma to prove. So again, don't worry, it's all not hard. At school, student can understand that. You just need to recall the things we did, and I will do my best to remind you. So, one more thing, we are going to use some function, as I'm telling now, and don't worry, it's something we're going to use without going into the details of why things are like that. I just tell you things you need to know, because these are not, again, theoretically, not combinatorially important things. So you just basically, you can definitely understand that. If you don't understand what I'm telling, that's a problem, then you need to ask. But if you understand that, don't worry that we will not go into all the calculations, because of course, if you do go into all the calculations, you will not have enough time to do the important stuff. So define C to be the lower integer part of the social cost of this equilibrium assignment A divided by the optimum assignment. So this is what we need to bound. We use the famous gamma function, which basically is known to be a complex extension of the factorial function. So we have the factorial function, which you all know, factorial of an integer number. For 0 is defined to be 1, and for any integer number larger than 1, it works only usually for non-negative integer. So for any natural number, factorial is simply the product of all the numbers between 1 and that number, including that number. So factorial of 2, for example, is 1 times 2. Factorial of 3 is 1 times 3, and so on. It's 1 times, excuse me, 1 times 2 times 3. You need to take the product of all the numbers. Now, there are multiple ways to extend it, of course, actually infinitely many, and there are many known ways to extend it. We are going to use this famous gamma function, which you don't need to know. I'll give you all the information you need to know here. That's defined for any complex number with a strictly positive real part as the integral. So the gamma of z of this complex number is the integral with the variable x of x to the z minus 1. Here z actually is a constant of inside the integral, times e to the power of minus x. And the integral is taken from 0 to infinity. And that's the definition. It can be checked, but we need complex integration, so we don't do it right now. That for any integer number which is strictly positive, for 0 it's not defined, as you can see, by the way. Because for 0 it's actually, for 0, wait a sec, why not defined? Well, first of all, we are telling it's not defined. We don't want to define it for 0. Second, for 0, if we use that formula for 0, it would be x to the power minus 1 times e to the power of minus x dx. It would be something. It would be something strictly positive. And 1 second. I'm just trying to see whether we will be able to tell something about that formula when we have z equal to 0. I don't see why not, but probably that's not equal to the 1. Yeah, it cannot be equal to 1 because we know that the integral of, when we get 1, so 1 will give you something equal to 1. So the integral of e minus x from 0 to infinity should be 1. I don't remember, but let's trust them. Because equalness x is, yeah, 0. Yes, exactly. It's 0 minus plus, yeah. So, okay. When z, I'm just telling you something you don't need to do yourself that now, but just to get some feeling. I'm just curious whether this function actually works for z equal to exactly 0. And I'm telling no, because for z equal to 1, it's going to be x to the power of 0, so 1, so just ignore this term. It's going to be the integral from 0 to infinity of e minus x dx. It's going to be normal real integral. Now, if you do this integral, and I'm doing this now in my head, then it is exactly 1, as we need to have, exactly to this, according to this formula. So in 1, it's going to be the factorial of 0, 1. In 0, however, it's going to be some different thing. Why? Probably it won't be equal to 1. But okay, actually, okay, it does not have to. Okay. Forget. It does not even have to be anything like that in 0. Because, so first of all, let me just finish and then just go back to the proof. Because I just have gone into something we don't need here. In 0, what we need to have is this function gamma extends the factorial in the sense that gamma of any positive integer number equal to this gamma of any k is equal to k minus 1 factorial. So gamma of 1 is equal to 0 factorial, which is 1. Right? Gamma of 2 is equal to 1 factorial, which is also gamma of 3 is equal to 2 factorial, which is 1 times 2, 2, and so on. Gamma of 0, even like if we ask what it does not mean anything, because the factorial of -1 is not defined in the original definition. So not only that we don't claim there is something here, that gamma is not defined for 0, because we just define it for all the complex numbers with a strictly positive real part. I remind you, the complex number has a real in that also does not have any meaning in this formula anyway. So just now, those who enjoy this attempt to see the meaning here, good. Those who didn't, just forget it. Let's go back. So we just define this ratio between the social cost of this equilibrium, time A and optimum. That's what we need to bound. Now we use the famous gamma function, which is defined for all the complex number with a positive real factor, positive real part as this integral, and it's known that they hold that for any positive integer, gamma of that integer k is equal to the factorial of that k minus 1. And the factorial of any non-negative integer is defined as I just told you. 0 is by definition 1, and then it's just the product of all the numbers between 1 of the integer numbers between 1 and that number increase. So that's something we have at our disposal, like in our toolbox. And we also use the fact that it's known that the inverse of the gamma for any probably non-negative real, all the domains we need is known to be of the order, up to a constant, of the order, I remind you that theta means of the order, of log m divided by log m. So it would suffice to show that S, this thing we need to bound, is at most gamma minus gamma, the inverse of gamma of m. And that's what we're going to do. That would actually, in particular, prove what we need to do. So, because that's known, the inverse of gamma is known to be of the order we need. Okay, now without loss of generality, now we're going to prove that. Assume that the machines are ordered such that the tasks are ordered. No, the machines. M machines. The speeds of the machines are such that the speed of the first machine is the largest, the speed of the last machine is the smallest, so the speed of the first machine is at least the speed of the second machine, so the order is non-increasing. And you know such an ordered list of machines, so first machine 1, second machine 2, and so on, to be L1 till M, not only the set, but also actually a list of machines. So there is an order. So the machines are in non-increasing order of the speed. Now, then, another important definition. For any k from 0 to c minus 1, I remind you what c is, define Lk to be Lk actually, I think okay, so I fixed some typo. Lk is defined to be as the largest prefix of this list, so the largest starting subset of this list. It may be empty, maybe the whole list, by the way. All the machines till the largest possible index in this list, such that all the machines between the 1 and this index are at least k times the optimum. So we look at the largest possible index, such that all the machines between 1 and that index are at least k times the optimum. It's not like that only Lk has to be at least, or Li, the largest index, has to be at least k times the optimum. No. Lk is defined to be as the largest possible prefix, such that all those between 1 and the largest possible, all those, without exception, are at least k times optimum. The lower of those are at least k times optimum, of course, under this assignment. And the next machine, we already have load which is strictly less than k times optimum. So the larger the k, the stricter the condition, the smaller the least. So Lk's are non-increasing with k. The larger the k, the smaller the least. In the book, you have some illustrations. Now let me just repeat. So let's assume that the list of the machines is ordered such that the speeds are non-increasing, and also then define this ordered list of machines by L, and then let Lk to be the largest possible prefix of machines such that all the machines in this prefix have load which is at least k times optimum. I remind that the load of a machine, in the case of uniformly related machines, is the total weight of the tasks which go there under this assignment divided by the speed. So we assume that there is this order, and we define this prefixes of L. And of course, if, for example, k is equal to 0, then this condition is, of course, trivial, because every load is at least 0. And therefore, Lk then is all the list. Because if k is too large, then it's not. So you understand the idea. The next is going to be very simple. We're almost done with the proof up to this recursion. So, as promised, I repeat the important stuff. So the C is what we are going to bound, and I mentioned that would suffice to show the C is bounded from above by the inverse of gamma, which properties we will use as we need. Don't worry, I'm not going to expect that you will conjure those properties by yourself. So C needs to be proven that, and that's enough because the inverse of gamma is known to be of the right order. I mean, that's the order we need. When we start the proof with saying order the machines by the speed, define this list L, for each k between 0 and c minus 1, I remind you what c is. We define those prefixes Lk, and what we're going to prove, that's the recursion, which we'll prove later, is that Lk is at least k plus 1 times Lk plus 1. Of course, as I said, Lk is non-increasing with k, so Lk plus 1 is generally smaller than Lk. So you cannot say that Lk is at least, excuse me, you can say that Lk is at least k plus 1. That's something which is immediate from the definition. But here we say something stronger. Lk is at least k plus 1 times the size of Lk is at least k plus 1 times the number of machines in Lk. And that's for 0 to c minus 2, and the size of Lc minus 2 is at least 1. Now, this is the recursive assumption we're going to use, and we're going to prove it immediately after. So using that assumption, we're going to immediately unroll that. So if you go look at the last one, is at least 1. The one before the last one is k plus 1 times the last one. Now k plus 1 is going to be c minus 1 plus 1 is going to be c times, at least c times 1, at least c. And they're going to multiply it many times. No. The last k is actually c minus 2. When k is equal to c minus 2, lk plus 1 is equal to ac minus 1. So this product is going to be exactly okay, so therefore this product is going to be the LC minus 1 is at least 1. LC minus 2 is going to be at least C minus 1 times 1. LC minus 3 is going to be at least C minus 2 times C minus 1 times 1, and so on. So it's going to be eventually this L0 is going to be the largest list, is going to be at least C minus 1 factorial, which by the property of the gamma function is going to be as we said, exactly equal to gamma of C. And since L0 is equal to L, because all the machines satisfy that their load is at least 0, the size of L0 has to be M, because it's simply all the machines. We have proven that M is at least gamma of C, therefore C is at most the inverse of gamma of M. And that's exactly what we need to show. C is at most inverse of gamma of M, because C is what we need to show to bound, and the inverse of gamma is of the right order. So we're basically proving this theorem up to proving that the recursive connection holds for Lk, and that's what we now need to do. We now prove the recurrent formula. Given that, we have proven the theorem. So first we prove the basics. Okay, let's just all right. Let's again repeat what we did. So we define the C, which we need to bound. We assume this also generate the speeds of the machines are ordered like that. And you know that such an ordered piece of machine is by L. Then for any k, between 0 and c minus 1, we divided a prefix Lk of L to be the largest possible prefix, such that all the machines there under the assignment have the load of at least k times. And now we need to prove the recursive formula. The first thing is the basis. So the size of LC minus 1 is at least 1. That's what we are proving. So that's simple. Assume by contradiction that it's not. So then it's empty. What does it mean? It means that already L1 does not satisfy the condition. So it's already not greater or equal C minus 1 times optimum. So L1 is already the load of machine 1. It's already strictly smaller than C minus 1 times optimum. Then, what we have, let's take a player which goes to machine J, which has a load of at least C times optimum. And I mentioned here that there exists such a machine, because if there exists such a machine, because C times optimum is the social cost of A. So some machine has to have such a load. So there exists such a player. There is a player who goes actually to a machine with such a load. Now, take this player I, then moving this player to machine 1, which we assume by contradiction has already a load smaller than C minus 1 times optimum, simply will make this player improve. That's the intuition. So if the load of the machine is so small and the speeds, I remind you, are ordered such that the speed is the maximum, it simply will benefit not any, but at least the player who achieves the maximum cost. The player, any player goes to the machine with the maximum cost, it will be beneficial for the player to move to L1. That will be the contradiction. That's why we will achieve a contradiction. Formally, moving player I to machine 1 will make player 1's cost suddenly become at more strictly smaller than what was already on machine 1, minus 1 times optimum. That was strictly larger than the load on machine 1, plus the size of player 1, of player I, divided by the speed of machine 1. Now, the Wi divided by speed of machine 1 is at most optimum, and here it should be Wi, not W1. Wi is at most optimum because the speed of machine 1 is the fastest. It cannot be that I put something on the fastest machine alone and it's already strictly an optimum. So it has to be at most optimum. Then the sum is going to be most C times optimum. So what we have proven is that player I deviating to machine 1 makes its cost strictly smaller than C times optimum. But we said that the cost used to be at least C times optimum. So player I strictly benefits, contradictory to the assumption that this assumption A is an Nash equilibrium. This assignment A is an Nash equilibrium. And therefore, this assignment is contradictory. So the size of L cannot be 0. So we have proven that the size of LC C minus 1 is at least 1. So we have proven what we wanted to do. Okay, so I fixed the typo I told you about. And so it has to be Wi divided by S1. And now we are done with proving this basis of this recursion. So we are now off to prove the second part of the recursion. That's the only thing we are left with. Having done that, we are done with the proof of the theorem. So we now need to prove that the size of Lk is at least k times 1 times the size of Lk plus 1. Now, mind the setting that we have this C, which we need to bound. We defined it. I really tried to remind it many times. I hope it helps. If not, please let me know in the comments. Without loss of generality, the size of machines are like that. We know increasingly. The Lk is this prefix, maximum length prefix, like all the lots within the prefix machine list are at least k times optimum. And we are proving this recursion. Now, we need now to prove something which will help us. So we prove a lemma now. So first, let A star define the denote the optimum. A, in other words, an assignment such as the social cost under this assignment achieves the optimum which is possible. That's the definition of an optimum. So now we relate the A, which is an equilibrium assignment, to a star which is not Q. Of course, theoretically they can be the same. Probably not. No, they can be the same because the process of stability is 1, so there is an optimum equilibrium. But don't have to be. So we relate this equilibrium assignment we fixed, and we are working with A to a star which is some optimum assignment we fixed. So what we prove is that if for task I, suppose that the equilibrium assignment sends it to Lk plus 1 to this set of machines, one of the machines in this set, one of the machines, then the assignment, the optimum assignment, will send it to Lk. Some relation between those. So if they cannot be too large, like too different, equilibrium and optimum. That's the intuition of what we are proving. Now, So how do we prove that? Now, if the difference is empty between L and LK, it means that LK is everything. So then a star, of course, goes to L somewhere, and therefore it has to be in LK, because in this case, just L and LK are the same. So then we are done. So we may assume that L minus LK is not empty, so there is something there. And so look at those machines which are not in LK, in other words, and denote the minimum machine there by Q. Remember that what does mean the minimum machine is the quickest machine there by Q. Since it's not in LK, it means, by the definition of LK, that slot is not at least K times optimum, but rather strictly less. So there we said that in a assume that of generality that L minus K set is not empty, because if it were, we would be able to immediately finish. So we assume it's not, and we take the first machine there, call it Q. It's not an LK, in particular, its law has to be strictly smaller than K times optimum. Now, we need to prove in the lemma, I remind you, that if A goes by A of I is in LK plus 1, the A star of I is in LK. Since we assume that A of I is in LK plus 1, it means that the log of a machine where I goes under A is at least K plus 1 times optimum. Okay, by the definition of L K plus 1. And now, notice, if Wi were at most SQ times optimum, Wi is the weight of I, the size of this task, in other words, and SQ is the speed of Q. Then, so if this weight had been so small relative to the speed of Q, then we would be able to improve what happens if we moved I to the machine Q. Because then the cost of I would be the current cost of Q times the Wi divided by the speed of Q. What would that be? Now we know that the cost of Q is strictly smaller, than K times optimum, because this Q is not null K. Now, since since we assume that Wi is at most CQ times optimum, then Wi divided by CQ is at most optimum. So this is at most optimum. And K plus 1 times optimum, by the assumption that A of I is in K plus 1, is at most the log of AI. So we have eventually managed, with all those assumptions, show that then if I makes to machine Q, its cost is going to be strictly smaller than its cost under A. Contradictory, of course, to A being in an equilibrium. Therefore, the assumption is wrong. So this is the wrong assumption. That was the assumption we made. Saying, let's see what would happen if it were so. So since AI goes to LK plus 1, it cannot be that Wi is at most CK times optimum, so Wi has to be strictly smaller than CK. Now we assume to the contrary that the lemma is wrong. So the A star of I does not go to LK. It goes to some J, which is not an LK. That's another assumption to the contrary. The first assumption we did manage to arrive at a contradiction, and then we conclude that Wi is strictly larger than SQ times optimum. Now we make a second assumption, which is basically what we need to prove. So when we arrive here to contradiction, we are done with the lemma. So the second assumption is that A star of I is not in LK. It's rather goes to some machine J, which is not null K. What does it mean? It means that the load of this machine under a star is at least Wi, the size of I, divided by the speed of this machine where it goes. Now, we have shown that Wi is strictly greater than SQ times optimum. So the denominator is strictly greater than SQ times optimum. And since SQ is at least as J, because remember how the machines are ordered, and as J is not in LK, and SQ is the quickest one, which is not in LK. So SQ is not lower than SJ. Therefore, this is at least optimum. And now we have arrived to the fact that the load under a star of J, of the machine J, is strictly larger than the optimum. We have strictly larger on the way of this inequality chain. Okay. This contradicts the optimality of A star. If the load of one of the machines is strictly larger than the optimum, it means that the cost of this assignment is strictly larger than the optimum. So it contradicts optimality, and therefore the assumption to the contrary was wrong. So the star of I does go to LK. So we did prove the lemma that if AI goes to LK plus 1, a star of I goes to LK. You don't have to see the intuition of the proof, just each step, but the intuition of the lemma, as I said, is that they are close enough. And then finally we are going to prove what we need to prove in the recursion. So I remind you that we are almost done. This is the last part of the proof. Yes. Now, how do we prove? What do we need to do? So, first we prove the theorem, assuming a certain recursive connection between LK and LK plus 1. I remind you that LK is the largest prefix of this list of machines ordered in a non-increasing order of speeds, such that each load under the assignment in question is at least K times optimum. And we proved what we need up to a certain recursion that the size of LK, not only is it at least as much as big as the size of LK plus 1, because the size of LK becomes smaller when K grows. The condition becomes strictly and strictly. But actually, the size of LK is at least K plus 1 times the size of LK. That's the important thing we need to prove in order to finish the proof of the theorem. Oh, we just finished the proof of a lemma. It will help us, and that if a task goes under the fixed equilibrium we are working with A to the prefix LK plus 1, then it has to go somewhere to LK and optimum. So LK in general is larger than LK plus 1. We know that it's not smaller, but it cannot go to beyond that. That's the idea. Now we need to prove that the size of LK has to be large enough. Intuitive, if it's not large enough, we'll have this contradictory. We'll have that too many machines, too many tasks go there, and it cannot be that too many tiles closing. So okay, let's see. For any machine in LK plus 1, by definition, the load is at least k times optimum. What does it mean? It means that the sum of the weights of the task going to that machine is at least k plus, excuse me, at least k plus 1. At least k plus 1 times optimum times the speed of that machine, because the load is exactly the sum of the weights divided by the speed. That's by definition of LK plus 1. Yes. Now summarize over all the machines. Let's see. Okay, we've done this for one machine LK plus 1, n machine J. Now summarize over all the machines in LK plus 1, and we get that the sum is at least this sum. In the sum in for all the machines in LK plus 1. Now the lemma above, remember the lemma, implies that A star assigns all this weight, A is assigned to LK plus 1, and A star assigns all this weight to the machines in LK. So the total weight of each machine is at least optimum, because A is optimum. A star is optimum. A star is optimum. Okay. And what does that mean? It means that this total weight is assigned, the total weight is assigned to machines in LK plus 1. Is at least that, and that has to be at most, not at least, at most optimum, because the optimum assigns it everything, assigns this to LK. The total weight of each machine is most optimum. So when we go over all these machines, we can just multiply by the speed of the machines and summarize. That has to be at most the optimum times the speed. It cannot be more. Otherwise, one of those machines would have a lot greater than the optimum, contradictory to the assumption that A star is optimum. Now some play with sums, divide by the optimum of G, then subtract the sum of SJs over LK plus 1. So divide the optimum. Then the left hand side, you subtract SJs. Yeah, so it's going to be K plus 1 times optimum SJ. Okay, optimum has been cancelled. So K plus 1 times SJ minus 1 SJ. So K times SJ, it's going to be only this. And the right side is going to be optimum again. Optimum has been cancelled, going to be SJs minus SJs, just at a sum. So the remaining sum is simply those who are in LK and not in LK plus 1. That's the remaining. Okay, we're almost done. Divide by S star the speed of the machine, which is the slowest machine in LK plus 1. Because the machines are ordered in a non-increasing order of speeds. The S of this in this place is the slowest machine in LK plus 1. It's the last machine in this prefix of L. Then the machine is, if the machine is in LK plus 1, its speed has to be at least the speed of a star, because the star is the slowest machine there. Even if a machine is not there, its speed is going to be at most the speed of a star, because that's going to be further down the list. And then you can just write S stars instead of S's. So if we go over all those y in LK plus 1, and we put S star instead of S, we get something even smaller. If you go over all those y in not in LK plus 1, in LK minus LK plus 1, and we put S star instead of S, Sj, we get something even larger. And then we get this inequality. From this inequality, we get this inequality. And then just get out of the inequality. Again, it's a lot of play with inequality. We get k out, the sum on the left hand side. So S, first of all, S star gets cancelled. Left hand side is just k times the size of LK plus 1. The right hand side is just LK minus LK plus 1. And that's exactly the same as LK minus the size of LK plus 1, because LK plus 1 is a subset. And LK, the size of LK, just moving LK plus 1, its size to the left. The size of LK is going to be at least the size of LK plus 1 times K plus 1. And that's exactly what we need. That's exactly what we need. So we have proven the second part of the main part of the recursion. And then I remind that means that basically I proven the theorem. Now, since you may have forgot the theorem, let me go back to show you the theorem. The social cost is at most some O times log of the number of machines divided by log of the number of machines times the optimum. So the price of anarchy is bounded by this slowly growing function. Okay, by the way, let me again go over the steps of the proof. So we proved the theorem using the recurrent formula. It was quick. And then we need to prove the formula. So first we prove the base of the formula. It was that the size of LC minus 1 is at least 1. And then we prove this connection, which also required some lemma. Okay, so we are done. And the next question is, what about the lower bound? So I promise you that we'll show that the upper bound is tight, asymptotically. So indeed, we can prove a lower bound. So given any number of machines, there exists a load balancing game with m machines and some number n, or a number n, most number of machines starts with an assignment which is an equilibrium which has a social cost which is theta. So it's of the order, not only bounded from above or below, it's of the order. Log m divided by log m of. So that's exactly the lower bound. The intention of the proof is that we construct an example of this A, and it's going to be an equilibrium because unilateral deviations won't help, because the other machines will be either too loaded or too slow. So it will be an equilibrium, but it will not be optimum, because there will be another way to improve that, have to rearrange things, and that will help, and that will help decrease the maximum cost, which will eventually help decrease which will thereby help decrease the social cost. So it's going to be an equilibrium which is going to be distance from the optimum by this factor. Okay, so the proof is simple. So recall the gamma function which we use. So which is defined for any complex number with a strictly positive real part. That's actually simple. Simpler the proof, then it's much simpler than the previous one. It has some technique in it. I'm sorry that the proofs are such technical, but that's simpler. Don't worry. So they're all simple. They may be complicated because of the multitude of details. So anyway, to define for any complex number, define the real part of this number for any complex number which has a strictly positive real part. We define this gamma. And all can be shown easily that for any strictly positive natural, the gamma of k is equal to the factorial of k minus 1. So this is basically an extension of the factorial function. Since the reverse of gamma is of the order we like so much, it's sufficient to demonstrate again with some equilibrium assignment. Of course, it's going to be in Nash equilibrium, not in N. It's going to be in NE. There's an equilibrium assignment. Such that the social cost, let me just show that it's not in N. It's going to be in Nash equilibrium. Such that the social cost of this equilibrium assignment is at least half times gamma reverse m minus 2 minus something which goes to 0 if you divide it by m, as m goes to infinity. That's the meaning of the O notation, times option. Now, do you understand what this means? Why that actually is something which suffices? If not, take a look. If you prove that, it means that the social cost of A is bounded by at least this factor from optimum. Now, this factor is basically gamma reversed minus 2 minus something which goes to 0 when you divide it by m. So this factor is theta of log m, because gamma reverse is theta of log m divided by log m. So is this expression. So asymptotically, that's the expression. So we need to find again an equilibrium such that the social cost of the equilibrium will be at least this factor times the optimum. Okay. 1 second. So define u as the floor, so as the integer value of gamma reverse of m divided by 3 minus 1. Which can be shown from the property of gamma is at least gamma reverse m minus 2 minus O of 1. And define Q plus 1 groups of machines denoted by group 0, group 1, till group Q as follows. Okay, that's the whole proof. It's not hard. So the proof is as follows. I've said sufficient to demonstrate a game in a Nash equilibrium such that, and again, it's going to be in NE, not in N. It's in E. Typo. So it's sufficient to demonstrate the game in a Nash equilibrium. The social cost of the Nash equilibrium is at least half the reverse of gamma minus 2 minus little O of 1 times of P. So we are defining now this game and this A. So we take this Q and define P plus 1 groups of machine. Now each GK group, the group K, consists of Q factorial divided by K factorial machines of speed 2 to the power of K each. Now A assigns K task of weight 2 to the power of K to each machine. So how much does it cost basically to run on this machine? K times 2 to the power of K divided by the speed, which is also 2 to the power of K. So it's K. Now the total number of machines it's not too many machines, right? We need to have m machines. The total amount of machines is just, okay, the size of gk is this q factorial divided by k factorial, so we can get q factorial out of the summation. Now this sum from 0 to q of 1 over k factorial can be shown by the definition of q to be at most 3. That's just calculations. Now, the property of gamma, remember that gamma of q plus 1 is exactly q factorial, so we can just replace q factorial by gamma of q plus 1. And again, using the definition of q, you can see that 3 times gamma of q plus 1 is at most m. Calculation. Now, since the sum of those, the sum of the sizes of the group is at most m, what if it's strictly smaller than m? We want an example of exactly m machines. What if it's exactly smaller than m? Then we just define more machines. We call them non-group machines. So out of any group, any of those q minus 1 groups, and they will be like the machines in G0. So the speed, that's in the sense that the speed is going to be q 2 to the power of 0, it's going to be 1. But our assignment, we also define here, does not assign them anything. We just define those machines to have m machines as we want. Now, example. Now, I think it's not the last part of the proof. My apologies. It's the penultimate slide. My apologies. I said you that it's the last one. No, it's the one before. Now, why is this A? We've defined an equilibrium. It's an equilibrium because no player can improve. So let's take some I who goes to some group GK. As I just said, nobody goes to a machine which is not in a group, so anyway, it goes to some GK. We said that how much it costs. It costs exactly K to run there, because there are K tasks of 2 to the K weight. So it's K times 2 to the K divided by the speed, which is 2 to the K. So it's exactly K times it takes for that task. So how could he possibly improve? Moving to a machine J with some J at least K won't reduce cost, because it already has cost of at least K for everyone who is there. If you move there, in addition, you will also decrease that cost. Increase the cost. It will definitely be strictly worse. Moving to a machine Gj with a J strictly smaller than K will also be a problem. One direction does not go because the machines that are slow, the machines that are not slow, they are not slow because they have too much already on their head. The second this direction, if J is smaller than K, is not going to work as we see now, because the machines, they are slow, their speed is not large enough. What is going to be the new load? It's going to be the J, the original load. For machine J, it's J, as we have calculated, times the size of this task, the 2 to the K, divided by the speed of the machine, 2 to the J. So it's J plus 2 to the K minus J. And using this nice inequality, 2 to the T is at least T plus 1 for any positive T, actually for any T at least 1, which you of course can check. So for T equals to 1, it's 2 at least 1 plus 1. And then we can just compare the derivatives and see that the speed of the growth of 2 to the T is always at least as much as that of t plus 1, which is exactly 1. So simply easily prove that. So we are therefore telling that 2 to the k plus 1 is at least k minus, 2 to the k minus j is at least k minus j plus 1. So it's the whole expression is k plus 1. Then the new load will be k plus 1. So you will also make a lot worse. So it's an equilibrium. You cannot move to any other machine. Now, final slide of the proof. So we need now to show that the optimum is far enough from what we have here. So I just remind you what we did. So we defined this Q, and we defined Q plus 1 groups of machines denoted by G0 till GQ. And that's how we define those groups. The assignment. Maybe we defined also groups we don't have any machine on them assigned to the, excuse me, we don't have any task. Maybe we find machines not in one of the groups. We do not have any task assigned them to prove that this A is a Nash equilibrium. Now, what is the social cost of A? The social cost on any of the machines is simply the social cost of a machine K is simply K. The load of machine K is simply K. So the social cost is the maximum load of between 0, 1 till Q, because there are Q machines. I have made a mistake. I wanted to say the social cost of a machine from group G, K is K. Because there are many machines possibly in each group. So the social cost, therefore, is maximum between 0, 1 until the number of groups Q. There may be also machines which are out of the group, but there is nobody going there under A, so they also have load of 0. The maximum is, of course, Q, and it's enough to show that the optimum is at most 2, because then the social cost divided by the optimum is going to be at least U divided by 2, and taking the expression for Q, I remind you Q is at least this one, so Q divided by 2 will be at least half of this one, and that's something we said it's enough for us to show, right? It suffices to demonstrate the game and energy equilibrium such that the social cost is at least half of this one times optimum. So it's going to be enough for us to show that there is the optimum is at most 2. There is an assignment which has the cost of at most 2. So consider the following assignment. For each of the K, 1 in Q, AI, if AI, there is A we have used, which we proved to be an equilibrium, is a machine in group GK. Now we assign I to a machine in group JK minus 1. We cannot indeed unilaterally decrease the load which a given task experience, but this whole rearrangement will now help us decrease the load. So if AI is the machine in JK, assign it now to some machine in JK minus 1. Since in total A maps, how many tasks does A map to some machine in JK? K task. Each machine is assigned K task. So K times the size of GK. This number of tasks is mapped to some machine in GK. The size of GK is Q star. Q factorial divided by K factorial. So it's K times Q factorial divided by K factorial. It's Q factorial divided by K minus 1 factorial. That's exactly the size of GK minus 1 by the definition. So we can, now when we are defining a new map. We can map one task per machine in gk-1. There is enough machines. And the load then is going to be at most the size of the task, k, divided by the speed of the machine in k-1, in gk-1, to the k-1, which is 2. And that's enough. Okay, so we've proven that the example we've shown, it has an Nash equilibrium and it has an optimum, such that the ratio is like we want. So this is the bound of log m divided by log log is asymptotically optimum. So in particular, it's not possible to bound by anything, the price of anarchy by anything constant. But we have managed to bound it by this asymptotical optimum, low growing function. Okay, the next topic is, of course, as you can guess, computed Nash equilibrium. So as we saw, for any load balancing game, the cyclographically decreasing, the sorted load vector is finite. It's a finite process. You still decrease the vector, so you cannot get back, and the number is finite, so the number of such vector is finite. So it's you have to at some point stop, and it means that you'll be at Nash equilibrium. So it's a finite process, but it's probably too long, or maybe it's not. In the case of identical machines, where we saw that every task can become unsatisfied at most once. If it moves once, we won't move it at more. Uniform related machines, we don't know of a short sequence of movements, which is also easily computed. So we need to do something else. The something else is actually an algorithm, just as a schedule algorithm. It's called LPT, largest processing time. It basically schedules the task, which is not kind of thought to be for Nash equilibrium, but likely it managed to compute Nash equilibrium efficiently, as we'll now prove. It goes over all the tasks in a non-increasing order of sizes, weights, in other words. And each task it inserts to a machine, maybe there are several such options, such that the cost the task will experience immediately after that insertion, so immediately at insertion time, will be the minimum. So it's linear the number of tasks. It's very quick. And now we are going to prove it's also a Nash equilibrium. So it's likely that we managed to use to have this algorithm do what we want. So this algorithm computes Nash equilibrium for load balancing on uniform rate machine. In particular, it computes a Nash equilibrium for machines which are equivalent, so for identical machines. So it's also an algorithm which works for identical machines. It also runs linearly in the number of tasks. Let's keep it in mind. So now we need to prove that indeed it computes Nash equilibrium. So assume 1 second. Assume the insertion order is 1 till n. I remind you that we go over all the tasks in the non-increasing or in a non-increasing order of weight. There are several such possible orders if you have tasks. And each task that goes to some machine where the cost it experiences immediately in the time of insertion will be minimum. So she assumes that the insertion order is 1 till n, without also generality. That's how we assume the tasks are named. You know, the time, by the way, of course, it's not really linear in general because you need to sort tasks in reality. So it's not really linear. But okay, this is kind of peanuts for us. But I'm just saying that if you really begin with the tasks, you don't know anything, you need to first sort them. Denote the time right after the insertion of task t by t. So by time t, we have just inserted the task t, and the whole set of tasks which have been inserted is 1 till t. Now we prove by induction that the partial assignment we have just built from t to the machines is an equilibrium. And then when we look at t equal to n, we are done. Now the basis is trivial. For example, we can look at t, which has not yet been before anything is inserted, so t being 0, or we also can look for t being 1. That task 1 goes to the best machine, basically the quickest machine, and of course it's an equilibrium. Well, when you look only at one task. Now the basis is trivial. The induction assumption claims the task 1 till t minus 1 are satisfied. No, satisfied. That those tasks are satisfied at time t minus 1. Now that's the assumption we had. Now we take a new task, t, which goes time t to machine j star. We need to prove that any other task from I which had been assigned to j star remains satisfied. We cannot do that it stops being satisfied. That's enough because the new task is at this moment also successful. Just assign it to the best machine. We could assign it at that time. So that task is satisfied. No task which is not in that machine can stop being satisfied because its cost has not increased, that and the cost of some other task on some other machine has increased. So the only thing which can happen, which could destroy the factor of equilibrium, is that one of the tasks, call it I, on the same machine where task T has been assigned, that task stops being satisfied. That's something we need to show it cannot happen. Why? It's simple. You know the total weight at time t at each machine, j by w by capital W. That's not just the weight of a task, that's the total weight. Now the assignment of t, excuse me, the assignment of t to j star minimizes the cost of t by definition. Moreover, since we go over the task in a non-increasing order of weight, and I was met before t, the weight of I is at least the weight of t. Now from those two conclusions that the assignment of t minimizes this cost, and that the weight of t is at most the weight of I, we now show what we need. It means that for any machine j, the cost that t experiences now it has to be 1 second. Okay. So the cost that t experiences now is of course the capital W in j star the total weight has been accumulated at time t at J star divided by the speed of the machine J star. It has to be the capital W. Let me fix that. So the total weight. By the way, in the book they confuse it a bit. They speak about load and they mean the total size. I think this is how I see it. If you read the book, pay attention and let me know if you think I'm wrong. Maybe the book is right and I'm wrong. So the total weight at J star divided by the speed of J star, that's the cost which the task T now experiences. It's at most the cost it would experience if it went to another machine, any other machine J, which is Wj plus its weight divided by J. By the definition of how you assign it, you assign it to a machine which minimizes the cost. Now, since the weight of T is at most Wi, the weight of I, you also have, okay, now it's what I wanted. We also have this last inequality. The weight of T is at most the weight of I. And what that means is that after assigning T, still the cost experienced by anyone on the machine J star, not only by T, but by anyway. So we look at this I, so the cost experienced by I on J star is at most the cost I would experience if it now moved to any other machine. So I remain satisfied, so everyone remains satisfied. The Nash equilibrium, the induction is done. LPT does compute Nash equilibrium. Now, it can also be shown, we don't do it, but it can be shown. The summation is the following ratios from the optimum. It's the 5 over 3 for uniform related machines, those with which we are now working. If the machines are known to be identical, the ratio becomes a bit better. You can promise 4 over 3 minus 1 over 3m for identical machines. Now, so this is also an assignment. This algorithm not only finds an equilibrium, but also finds something within a proven ratio, constant ratio from the optimum. Now, what about finding an optimum Nash equilibrium? Now, don't hope for an optimum algorithm even without an equilibrium. Since just finding an algorithm for Makespan is NP hard. So finding an optimum Makespan is NP hard even for identical machines. What we can do is that we have a p-task. It means that for any given epsilon, we have an algorithm which approximates with at most epsilon 1 plus epsilon ratio. And this time is polynomial, but the epsilon may be in the exponent. So time is polynomial in the other set. So you have a reasonable, you have an arbitrarily good approximation, but the time is not always behaving well with respect to the approximation factor. So there is this old p-task by Hochbaum and Schmois from 88. Now, it works for uniformly related machines, and it may result, however, in a non-equilibrium assignment. So for us, if you not only want to maximize them, to optimize Makespan, but also want an equilibrium, it's not. However, there is an algorithm by Feldman from 2003, which basically takes such an assignment and converts it to a Nash equilibrium without increasing the Makespan. And that procedure is called Nashification. So you make something Nash equilibrium. Okay, now we are going to the next topic.